Thank you for inviting me to be here. I wish I could be there physically, but this will have to do. I'm a stellar spectroscopist. It is my job to actually provide abundances. Colleagues and I provide abundances that will help guide nuclear astrophysicists. And the picture on the left, upper left, is where we would all like to be, with a complete understanding of how the universe started, as Jordy was talking about, with hydrogen, helium, and a little lithium, and end up with the entire periodic table. What I deal with is the picture on the right. I have to decode the spectrum of a star and try to get chemical compositions at the surface layers of that star. Okay. A few definitions first. I will be talking about a specific age in our galaxy to be introduced first, but in observational lingo, typically our galaxy is divided into populations, historically going back to, I guess, before 1950. Well, we have now the so-called thin disk, we have the thick disk, and a term that's gone out of favor is called the old disk and the bulge. Then we have the halo, and there are various types of ways you can discuss the halo and the disk: inner halo, outer halo, accreted component, dissipation component. There are various ways you can figure out what populations things belong to: kinematics, chemical compositions. You can look for subpopulations, and that's what I'll do. Is in 45 minutes, I can't discuss anywhere near all of those. So I'm just going to focus on one particular kind. Abundance definitions, they are by now pretty standard in all stellar spectroscopy, but coming from nuclear physics, you may find them relatively new. The one that most people know already is the bracket notation. That's the second definition. X to Y, which is basically a comparison of the number density ratio logarithmically in a stellar atmosphere compared with that same ratio in the atmosphere of the sun. It's a differential measurement. How different is an abundance ratio compared to the solar value? Less standard, but now becoming pretty normal, is to talk about log epsilon, which is more of an absolute number density. It's referring to a particular mix in a particular star. That is, again, base 10 log of element X, number density compared to hydrogen plus 12. So this is on a hydrogen of 10 to the 12th scale. We talk about metallicity. Metallicity, for all intents and purposes, is thought of as the iron to hydrogen value for spectroscopic reasons. Yeah, iron transitions are all over the spectrum of almost all stars, and it is very convenient to define the overall element content by the bracket iron to hydrogen ratio. There are various adjectives you can place on iron to hydrogen metallicities. You may choose whichever one you want, and I won't care. Metal poor stars, to me, start at about metallicity of minus 0.5. That's a third of the solar overall iron abundance. Very metal poor, minus 2. That's a 100th. Extremely metal poor, minus 3. Nature quality metal poor, minus 6. And the adjectives could just continue. I don't care anymore about this. I'm talking about metal poor stars, because what I want to concentrate are on the stars that were born near the beginning of our galaxy. Here's a standard cartoon to describe where the various populations happen, and the so-called globular clusters are part of the halo population of stars. They won't enter into our discussion today, but note when I'm talking about metal poor stars, that would include stars in globular clusters. These are ones that various arguments over a century of discussion have decided that they're among the oldest stars, the first formed stars in our galaxy. Why am I going to concentrate on those stars? Because they're simple. That is, the Holy Grail, of course, is to be able to begin a chemical evolution, nuclear astrophysics discussion, understanding that the Big Bang produced hydrogen, helium, and lithium, and end up with the solar chemical composition. That involves an awful lot of input and output. As you see here, there's, I guess, first Bernard Padgel made this kind of diagram, and there are various contributions. But if you begin with a study of the oldest stars born near the beginning of our galaxy, most of the boxes here don't count. There is not much chemical evolution between the beginning of our galaxy and the formation of a star out in the galactic halo that is a 100th or 1,000th of the solar metallicity. These are stars that are products of the actions of one or at most very, very few nucleosynthesis events, and we're looking at more pristine material. That is easier to work with than most of the solar chemical composition. Let's see. I am now stuck here on my slide. There we go. The next slide. All of the work that I do, I'm going to just leave at one slide. I'm always looking at high resolution stellar spectra. You see some examples at the top there over a broad spectral region from blue to red. And in the right-hand middle picture, those spectral absorption lines can be a bewildering, complicated mess. But fortunately, it's an understandable mess. A lot of work over a lot of decades has served to basically identify most of the prominent spectral features in the sun and other stars. And there are still gaps, and they should be thought about. But a cartoon due to Bengt Gustafsson of the whole process that I undergo is a comparison between synthetic and observed spectra. I won't go any farther than that. You can see that this involves an awful lot of input, basic model assumptions, model calculations, analysis of line formation. I can't really do anything more than that here. I refer to those of you who are coming from outside stellar spectroscopy that a wonderful book sort of taking care of most of the questions you might have is David Gray's textbook, Stellar Photos, Observation and Analysis of Stellar Photospheres, now in its at least second edition. There's a way you can basically, that could be a Bible on your shelf if you want to find out about chemical compositions. When I look at a stellar spectrum, when you look at a stellar spectrum, it is pretty easy to figure out the overall level of the heavy elements. As long as you model, and it's a physical state, of course, in the stellar atmosphere, as long as you model what has gone on in the atmosphere of the star. What has gone on means what's the temperature? What is the gravity? What are the turbulent velocities? And after you take care of those, and there are various ways to do them very well, then what's left is the overall level of the heavy elements, which I think you can easily see from the top, which Jacobson et al. Said was a red giant star, 4,700 degrees, gravity 1.1, metallicity of -1.6. Now that's metal poor already. That's more than an order of magnitude fewer heavy elements than in the sun. But that looks really grossly metal rich when you compare it to the bottom one, which is down by another 2 orders of magnitude in Fe to H. And remember, the logarithms will lull you to sleep. -3.8 means 1/10,000th of the heavy element content of the sun. And the heavy element content of the sun by number is only about 1%. So we're talking about a very, very clean atmosphere. You're back to nearly all hydrogen and helium. There are various things you can do. This kind of picture has been shown by Jordi already. Fortunately, a lot of work has shown that there are various parts of the abundance diagram that we can now attribute to various processes that have gone on in light and heavy stars as they died and gave their elements to the next generation of stars. In particular, I want to talk about the so-called neutron capture elements, which I will define in more exactly in a second. And I want to talk about the iron group elements, the ones that all of us should know. Neutron capture elements, most of the periodic table, not by number, but by name the elements. Anything heavier than zinc, element 30, is generally considered to be dominated by capturing neutrons either quickly or slowly and building the rest of the periodic table that way. So we're talking about most of the periodic table. There's a very nice, in other words, most of you who are coming from nuclear physics should know already the Rolfs and Rodney text. They have some elegant figures there that describe the difference in kinds of neutron capture events that make the heavy elements. They generally are divided more sharply than you might imagine between the S process, that is slow neutron capture in order to allow available beta decays to occur, and the rapid R process, which is basically a blast followed by furious decay back to the valley of beta stability. My first of my self-criticisms of stellar spectroscopists is we tend to talk about the R or the S process elements. That's wrong. When I talk about an R process element, I really mean one whose solar system abundance has been dominated by one of these processes or the other. That's sloppy. There's another nice figure. I won't spend too much time on it, but it's an elegant way to talk about what isotopes of what elements can exist in the slow and the rapid process. In the solar system, meteorologists have done a nice job of separating the elements, and then nuclear astrophysics folks have been able, isotope by isotope, to assign pretty well the amount of each isotope that has been created prior to solar system formation by the rapid neutron capture process, the R process, and the slow process. And the fortunate thing is that although both processes can contribute to most of the heavy elements, that there are glaring dominances by either the R process or the S process. In particular, rapid neutron capture processes dominate the production of things like europium, element 63, dominate the third neutron capture peak, osmium, platinum, and gold. And those things are observable. And they also, our process also dominates a couple of elements that are very, very difficult to observe spectroscopically, tellurium and xenon. Whereas the S process, if you find a large amount of strontium or a large amount of barium in a star, that is a signal that the S process has been at work in creating the mix of elements. Lead is another one. More about that later. You look at spectra of low metallicity stars. You've already seen a few of them. What was a surprise in the early 90s was the discovery that many halo stars, many very low metallicity stars, have a freakish overabundance of those elements which are attributable to prior synthesis in the R process. In particular, the one element you look at in the blue spectral range that tells you right away is europium. Here are two stars. They are bad spectra. We can do much better nowadays, but in the early 90s, this is what we had from a Carnegie survey. And it is simple. I love projects in which I cannot mess up the answer. Europium, now you see it, now you don't. And it's a gross effect. And we've found stars like this all over the place. Moreover, as the spectra have improved and other things have happened, which I'll talk about in a second, we've been able to map out a huge number of elements, particularly among the lanthanides, and find that element to element, there's a beautiful match in an R process rich star to exactly, almost exactly what you find in breakdown of the solar chemical composition. It's the R process appears to be universal. Now, how did I go from the bad spectrum you just saw before to the elegant looking one now? Well, bigger telescopes came out, better instruments. And the one thing that I want to plug, and forgive me because I've helped out on this, but it's not been my work. You've got to understand what laboratory atomic physics has done. I would be surprised if there are many atomic physicists in the audience today, but the atomic physics deserves a real shout out. I've worked with the Wisconsin group. They do lab astro, and they have been responsible for the huge improvement in transition data for a number of elements, both in the iron group, that's below, and among the lanthanides. And they and the people at Mons and London and Lund and Liège, they all deserve a huge amount of credit. Any stellar chemical composition analysis can't be any better than the basic atomic transition data that it uses. And these folks are of great importance. Okay, so I had this thing for one star. It looked like a perfect match to the R process, not the S process distribution. Now you search for other R process rich stars and you find a lot of them. And what do you learn after you find this? Well, I'm going to just give you really a bullet point discussion here. I want to talk about star to star. I claim the overall pattern is something that is so dull that I don't want to work on it anymore. I want to point out, however, that the overall neutron capture elements, no matter where they come from, they were here in our galaxy at a very early time. And I'm going to talk about thorium and uranium and the lighter elements and stuff like that. Okay, so on to the show. There's a review in Review of Modern Physics by Cowan et al. That just came out. And here are a number of different R process rich stars. And matching each one of those is just the R process distribution of solar system abundances. They're all the same. There's nothing more to say in especially the lanthanide element group. In the top panel, there are individual matches. In the bottom panel, there's the deltas. That is, how do all these compare? You do an average over 13 stars, and you say, well, I don't have anything more to say here. They're all like the solar. And the beauty of this is, of course, that whatever made these elements at the beginning of the galaxy before low metallicity stars were born is exactly the same kind of process that built the neutron capture R process distribution all the way up to the formation of the solar system. Another point, which is not talked about as much as it should. There was a modest paper by Ian Roederer in 2013 in which he just simply asked, well, can I find low metallicity stars without neutron capture elements? And without worrying about the details, barium and strontium have intrinsically strong absorption lines. And so he used those and say, well, can I trace back lower and lower metallicity? At what point do I miss the neutron capture elements? And the answer is never. Given a good enough spectra, good enough signal, good enough resolution, they're always there. They may be very small abundances, but they are there at extremely metal poor stars. The galaxy did this right away. That's the takeaway message there. Uranium, thorium. We were very excited when we discovered, and you can discover it very easily in R process rich stars, transitions of thorium. That's relatively easy to do. The big excitement was when Vanessa Hill and her collaborators, Roger Carrel, et cetera, discovered the single line of uranium that is accessible in metal poor stars. That's the breaks, folks. You just can't choose where the atomic physics puts the strong lines and the weak lines. So here is the single line everybody uses, 3859 angstroms. It's in a messy region, but the discovery is irrefutable. The nice thing about using uranium and thorium in a very metal poor star is that you know only one or a few prior nucleosynthesis events happened. They had to be explosive, otherwise you can't produce elements 90 and 92. And then the clock starts. These elements created, let's call it one supernova or one something else, binary neutron star condensation, whatever. Whatever happened, those elements, including the radioactive thorium and uranium, are thrown out in the interstellar medium. They're gathered into the stars that I now see as our process-rich stars, and nothing else matters. There have been no reprocessing. There are no losses, no new star formation you have to worry about. You don't have to worry about the interstellar medium. It's just the clock ticking. And therefore, in principle, ratios of thorium to uranium can give you a chronometer for the galaxy. I just simply show, and we only know a handful of uranium detections. And if you look at the bottom middle one, you say, I think that's a detection, but maybe not. So you should keep healthy skepticism, but there are too many detections, all 7 or 8 of them now, such that, yes, we have detected uranium. Yes, you can do cosmic chronometry. And yes, you get roughly the age of our galaxy. Unfortunately, you get a large error bar on it. So it's confirmation, but not a superior proof about the age of our galaxy. Next topic in the R process elements. Suppose you look not at the most extremely metal poor stars, metallicity -3, whatever, but if you look at others, you look at the entire metallicity domain that matters to most people, that is solar, FeH of 0, down to say metallicity -3. Notice that the ratio of light elements, strontium, yttrium, zirconium, 38, 39, 40, to barium, element 56, the ratio starts scattering. And we don't quite yet know what it was. There was a paper by Claudia Travaglio that, because it was so frustrating without good theory to back up why the scattering increased in the light to heavy, that she and colleagues called it lighter element primary process. Having been on that paper, to my embarrassment, that LEPP still exists. LEPP means we don't know what's going on. Various possibilities are a weak S process, explosive helium burning, the I process, neutrino-driven wind, probably 5 more bullets. I've shown you the R process rich stars. How about the R process poor stars? They're not actually R process poor, they're N capture poor. That is, there is an underabundance of neutron capture elements compared with things like the iron group. Well, they're around. They're more difficult to work with spectroscopically, because underabundances mean weaker transitions, almost to the limit of undetectability. So there are a few stars, and their names don't mean a thing here now, so ignore them, in which you can show easily that the signature of the neutron capture elements is an R process. That is, the healthy amount of europium, the europium to barium ratio is fit sort of, europium, barium, lanthanum, it sort of is fit by an R process distribution. But there's this dramatic drop off between the lighter elements like strontium, lighter neutron capture elements like strontium, to the heavier ones like barium and europium. And it's just like things are just falling off a roof. It probably means that, again, this is me reporting, and all you folks in the audience who do nuclear astrophysics have to grapple with the effect of the problem that not all our process events are the same. Looks like there's a cutoff on some of them. It's up to the stellar modelers, stellar and neutron star merger folks. You must figure this out. Do not neglect this effect. For every R process rich star, there are some R process weak stars, S process weak. So I'm going to show you those in another minute. And what we've done here is realized that looking for stars one at a time and analyzing them one at a time is not an efficient way to figure out how common the R process has been at the start of our galaxy. So a bunch of different people under the leadership of Tim Beers made so-called R process alliance, which involves getting tons of spectra with many high-resolution spectrographs at many observatories, all for very metal-poor stars, to just look to see what these things like europium to iron really are. The goal is about a couple of thousand stars, and we're about halfway there. And so let's see what the statistics are. Oh, sorry, first, you need high spectral resolution in order to detect most of the strong R process elements. Europium, lanthanum, dysprosium, they're kind of intrinsically weak. The good news is that when they're overabundant, you don't terribly need high signal to noise. Here's an example of an exquisitely good signal to noise spectrum of a star that was in the previous slide, but that has weak neutron capture elements compared with a very noisy so-called snapshot spectrum that of an R process rich star. Well, R process rich star, I could remember seeing as that spectrum came in, the 4129 line of europium, it just was screaming at us. We could see that right away. So this is not a difficult problem. It's just one that takes some time. And given about 600 stars so far, not only observed, but reduced and analyzed, here are the statistics for europium to iron ratios. And remember, this is a surrogate for the R process. What do we detect here? What I think is again, the message that reinforces what I said earlier is that, hey, there are an awful lot of R processing going on in our very early galaxy. We must account for that. We can do better, and I'm going to leave it here. There is some structure in the observed abundances that might be good for further study. And I'm going to leave it there, but things like barium to europium, things start happening that are different when you have a low amount of europium. I'll leave it at that. But in other words, there's more information there. The final big point here, remember, star to star, the enormous R process or the enormous europium variation, not like things like magnesium. It's just star to star. You cannot predict what the neutron capture elements, and in particular the R process, will bring. That's why you do it one star at a time. I finally just have to breeze by this. Simply a reminder that R process rich stars have been found in nearby dwarf spheroidals, several inside a reticulum too. CG et al., Brower et al., people like that. I don't have time to do this, but this was happening in other galaxies. There are some stars which are low metallicity, but they are showing clear enhancements of carbon and those neutron capture elements that are enhanced by the S process, barium, lanthanum, lead. Almost all of them are binaries. And here's what they look like. I gotta have a spectrum here. I'm a spectroscopist. So the left-hand picture shows how grossly large the lines of lead can be, element 82. On the right-hand side from that same paper, which I'm embarrassed I forgot to cite here, but I'll fix that. And that same, oh, there, okay, et al. 2002, there's an attempt to fit the distribution of elements. And the thing to note especially is the monster amount of lead that's created. In 2008, there was an annual reviews article that I wrote with John Cowan and Roberto Gallino, in which several stars with carbon enhancements and S-process enhancements were sort of fit. And what's happening here is the following. I have to do a quick interpretation. We see these stars that are S-process rich and carbon rich. We see that they're binaries. Generally speaking, we cannot find their companions, which gives you the obvious scenario. A star became a giant, and then say an active asymptotic giant branch star, and mixed interior products to the outer envelope, where as it cast off the outer envelope as a planetary nebula, some of its material was sucked onto the star that we now see today, enriching it, a very ordinary star with these enhanced products. In order to understand the process in detail, that is creation in the star that's now a white dwarf, and what its envelope and interior characteristics were, what were the factors involved in it transferring elements to its companion star. There are an awful lot of things you have to adjust here. I list some of them. I'm sure there are more. Roberto Gallino could spend an hour and a half discussing this one picture. But the point is not how complex and how many knobs you have to turn, but the fact that you can do it at all. And it's very convincing on what actually happened. So we have stars that were born ordinary, no big R process enhancements. They made their own show by one of the stars donating its aging material to the star that we're now looking at. I have about 15 minutes left. And so now my final topic. Iron group. My definition of the iron group is scandium, element 21, through zinc, element 30. These are naturally very abundant, as Jordy talked about. And they're all over the place in a stellar spectrum. They're easy, relatively easy to answer. Why am I even talking about these? Shouldn't these have been solved for good abundances years ago? Well, not really. The problem was, again, bad spectra, bad observational techniques, bad analytical techniques, and terrible lab data. All of those are in much better shape than they used to be. So this is the story about going back after all the easy victories in looking for R and S-rich stars near the beginning of the galaxy, and now trying to say, look, what about the ordinary iron group elements? One of the reasons to do this is that modelers like Kobayashi et al. 2006, for example, have been able not only to predict that, yes, these elements would be made in massive stars, but predict abundance ratios. So this you ought to be able to confront these nucleosynthesis theories for the iron group and lighter elements. You ought to be able to confront them quantitatively with good stellar abundances. And when they started to do this in the 90s, things looked very interesting. That is, what you're seeing here now are ratios with respect to iron of chromium, cobalt, manganese, and copper. And remember, these are relative abundances with respect to the solar ratios. So right away you say, wait a minute, as you go to very metal poor stars, they have very low chromium abundances. They have very high cobalt abundances. They have really weak amounts of manganese and copper. So Andy McWilliam published this figure in a 1997 review paper. And then the so-called First Stars group, which again, Vanessa Hill, Roger Carrel, the Speets, folks like that, they did a very, very nice job in getting much better spectra, doing a more careful analysis. But what they found was the same thing. They found large cobalt abundances in metal poor stars and very poor, very low chromium. there was a problem. And Chiaki Kobayashi showed this in her 2006 paper right away. Well, what chromium? In the top right panel, there is the chromium to iron ratio that you would get if you used neutral chromium lines and neutral iron lines. Yep, chromium is low in metal poor stars. If you use ionized chromium and ionized iron, there's no problem. The chromium to iron ratio stays at 0, the solar ratio. Now, folks, there's only one number of chromium atoms in a star. You can count them. Well, you can't, but if you could count them, there's only one answer. It cannot be right that you have these two pictures and both of them be right, or either of them right. First thing you have to understand, the stellar spectroscopist really should be looking at ionized transitions, not neutral transitions. The stellar spectroscopist had better understand that in very metal poor main stars, when lines are being formed, absorption lines are being formed, effectively everything's ionized in the iron group. The number of atoms is really dominated by the ions, not the neutrals. So you should be careful. Not only that, you should be obeying Sutton's law. Willie Sutton, no one's sure whether he actually said this, but he was a famous bank robber in the United States. And the claim is that he was once asked why he robbed banks, and he said, well, that's where the money is. And in that sense, knowing that if you want to count atoms of the iron group, you had better look at ionized transitions. Where are the ionized transitions? They're in the near ultraviolet to the ultraviolet spectral region. Again, it's pure atomic physics. So you need to go where the ionized lines are. You need to use the spectrograms to get down to the atmospheric cutoff at 3,000 angstroms, and you need the Hubble Space Telescope. I give you an entire survey of this effort that a group that I've been working with has done with HST, high resolution spectra on very metal poor stars, all 4 of them. You cannot ask Hubble Space Telescope to give you a sample of 100 stars with high resolution, high signal to noise spectra in the ultraviolet. You simply won't get the time. You got to do these one at a time. But the good news is that with this simple survey of stars in the metallicity -2 to -3 regime, there are new results, and they don't look like the old results in McWilliam at all. Oh, sorry, honesty. I was a co-author on McWilliam et al. 95. So I'm blaming myself. I was wrong. So the abundance distributions in X to H values are given for all 4 stars on the left. But look, just concentrate on the plot on the right. Where is the chromium deficiency? It doesn't exist. Where is the cobalt overabundance? We don't think it exists. Is there a zinc overabundance that early universe people would like to worry about? Yeah, probably, but I'm not sure of that. But what a difference from old ideas are the scandium, titanium, and vanadium abundances. These are the lightest elements in the iron group. And these are ones that most people have not talked about and need to in the future. Why have people not much talked about them? Because titanium is overabundant in metal poor stars. Yeah, we knew it was an alpha element. Baloney. So just looking into, once we discovered, hey, it looks like scandium and titanium and vanadium are all overabundant in these 4 stars. Then we started looking at surveys which had been done in the past. It turns out that the scandium to titanium correlation is in everybody's survey. It's just that the signal was weak and people didn't pay attention to it. But it's all there. Whether you do survey by survey in the left, or you look at a grand summary on the right, as scandium goes, so does titanium. maybe as titanium goes, so does scandium. They are correlated. Vanadium is a little more difficult for spectroscopic reasons, but yeah, it's the same thing. Vanadium and titanium and scandium all correlate. To be sure, if you go to, say, a heavy iron group element like nickel, and you compare that to titanium, there's no correlation whatsoever. So this is definitely a thing which is characteristic of the lighter elements of the iron group.
Sorry to interrupt, Chris, that is your 5 minutes warning.
Thank you. I'll be right on time. Let's first deal with titanium. I am guilty. Almost every stellar spectroscopist has been guilty of this sin, calling titanium an alpha element. An alpha element is an element whose dominant isotope is even numbers of helium nuclei. That works for neon, magnesium, silicons, sulfur, and calcium, not for titanium. Titanium is element 22. 2 times 22 is 44. It doesn't exist. Well, it exists for 63 years. The dominant titanium isotope is 48. Titanium is not an alpha element. The reason why it was called that, it's overabundant many times in metal poor stars, just like calcium is, just like sulfur and silicon are. So we all got lazy. Oops. Where does all this happen? I simply want to throw one thing, refer you to a very nice paper by Curtis et al. Trying to explain the iron group. Curtis et al. Has some nice tables describing what they believe to be the layers of the star. Jordy was talking about the internal constitution of high mass stars, but they have a nice table there on suggested origins for each of the elements we see at the surface. But I end there by saying, why should I care? That is, my job is to get reliable abundances. I am not responsible for what you people do with them. That is, and it's a challenge. What I mean is, you must demand of me that I produce abundances that are rational. If I don't give you reliable abundances, you're wasting your effort on nuclear astrophysics. I have the duty to give you abundances I can believe. And I'm embarrassed to say that has only happened recently for fundamental elements like iron and magnesium and silicon and scandium and titanium, okay? I turn it over to you. With this summary, we believe that we're on to something new with the iron group elemental abundances. We believe that this will help nuclear astrophysicists. And in particular, there's been an awful lot of theoretical work to try to explain the large cobalt to iron abundances at low metallicity. And the embarrassing thing is, I think that may not be what is real. And it's not the folks who do interiors of stars. It's the spectroscopist's fault. And we've got to keep working. But that is, nuclear astro people, as I say below, need us to certify the light elements and the heavy elements. So we've got to keep working our end of the bargain. And I'll leave you with one final thing, which I remember from a long time ago at a meeting, because it just stuck with me. This is by Pierre Magan, who doesn't do chemical composition work anymore, but back then he did. He basically used his meeting time at Liège in the early 90s to issue a challenge to stellar spectroscopists. You can read it, but the bold thing is it's a matter of work. And it needs a lot of people to do a lot of work in a lot of areas. It needs good stellar models. It needs good radiative transfer. It needs reliable atomic physics. All of this needs to be done, and it is a matter of will. So be careful, the folks out there. Make sure you understand the stellar abundances that you desperately try to understand do have an error bar on them. And it is our duty to define clearly what that error bar is and to warn you about places where we're not sure that we have the right answer. To be continued. I wish we could get lots more data for Hubble Space Telescope in the ultraviolet, where an awful lot of the rest of the periodic table is hiding. And we can't. We can do beg for 1 or 2 stars at a time, but we should be going all over those spectra with a fine-tooth comb. Thank you for letting me talk to you folks.
So question 1 is the following. What is the biggest uncertainty in evaluating stellar spectra?
You want a joke question, or do you want, I mean, the joke is yes. That is, let me suggest that what isn't as crucial now is ever higher resolution spectra. I think there are really good spectra of really interesting stars that are now in the various archives. That is, yes, we should keep looking for more peculiar stars. We should keep looking for good spectra. But the observed spectra generally are good enough to answer most of the major questions. Again, my plea for more ultraviolet, but well, what can we do about that? 20 years ago, 25 years ago, the atomic physics was in terrible shape. And again, folks, these people get no love whatsoever because the average attitude in most physics departments in the United States is atomic physics was solved by Niels Bohr, and now we can go on to more interesting topics. And it really takes an awful lot of dedicated, working with atomic physicists opened my eyes to care in analysis. These are the most painstaking folks you'll ever meet. But that's happily getting much better. I would think then the current things I am most nervous about are things that folks in Europe are doing a lot to solve. People like Karen Lind, Martin Asplund, Maria Bergaman, working on departures from standard analyses, in particular, departures from plane parallel static atmospheres, single slab atmospheres, or single stream atmospheres, and how light travels through the atmosphere. Departure from a local thermodynamic equilibrium. I would think that hopefully in the next 5 to 10 years, an awful lot of that for the transitions that we care about for getting good chemical compositions will have been solved. That's in quotes, but it's really where a lot of the work happens. And it's a lot of work happening right in Europe right now.
Yeah, and I think there you mentioned Maria Bergaman. I think she did a non-LTE modeling of chromium-1 lines and could show that they get into much better agreement with the chromium-2 lines, for example.
Indeed, yes.
Yeah, yeah.
As a matter of fact, just sort of if you take naively, if you simply take her corrections, and these are from a decade ago, if you take her corrections and apply it to the chromium-1 lines as observed now, most of the chromium deficiency just simply disappears.
That's correct. And it's not surprising that the chromium-1 lines suffer from non-LTE effects either. So question 2 here. What is the interpretation for cosmochronometers yielding ages that are vastly larger than what we take to be the age of the universe, E.G.60 gigayears?
I have to understand what.
So there are some stars that simply turn out to become way too old when you use standard cosmochronometers, radioactive age dating.
And a few of them turn out to have been born yesterday.
Exactly. They have negative ages. Yeah.
There are stars. The tail of the dog is the stars are the elements thorium and uranium, way out in the actinide group. the ratio of the production ratio of the actinides to say the lanthanides is quite variable. But if you, that's why it is absolutely essential that spectroscopists get thorium and uranium. Then the problem is the age you derive is basically e to the abundances. That is, these are logarithmic abundances, but look, if you want an age, you have to compare the decay of uranium and thorium, and that involves an exponential. That means that whatever abundance uncertainties that you have in that ratio propagates in a substantial way into a derived age. Therefore, if anybody says, well, I get 16 gigayears for this one star, and I will say, okay, that's within the error bar, and I wish it weren't so, but that's why uranium thorium has not become the primary cosmochronometer.
Right. Yeah. It's not our best age component age estimate, unfortunately.
We're just happy that it is mostly in agreement.
Exactly. Yeah. I'm hopping over one question. We'll see whether we come back to question 3 here. Question 4 is, does the star-to-star variation of europium to iron have any relation to the star's location in our Milky Way or their kinematic properties? I'm sorry.
Yeah, that is under study right now. If I had a screen, I could refer you to a paper in the Beers group that discusses this very point. I know that in the past, Ian Roederer has claimed that the kinematics of some of the R-process rich stars suggest that they are not native members of a galactic halo, and they may have actually been captured from nearby dwarf spheroids. Now, if that can be sustained, that's an interesting new fact. However, remember, folks, all that does is just move the problem to the next galaxy. The problem still is there, but now we've just said, oh, don't worry about it. These are just visitors to the Milky Way.
Okay, question 5. What plots of neutron capture element abundance observations? I'm starting again. Most plots of neutron capture element abundance observations start with strontium. What do we know about the element's origin between zinc and strontium, and what makes their detection maybe more difficult?
Yes, and not only that, but in another sense, the elements from 49 through 55 also, there are very, very few observations of them. And the entire point is, let's go back to Jordy's talk, the periodic table, atomic physics, atomic structure. It is that we cannot force matter to absorb at the wavelengths we want with the strengths we want. And therefore, if you go down, and that's one of the reasons why begging and pleading with Hubble Space Telescope people is still a good idea for low metallicity stars. We would love to even go beyond. We have like 1 or 2 stars that actually we have very deep UV observations. That's where a lot of these other elements will have stronger transitions. So it's a pure atomic physics problem. If I tell you that I don't know selenium, it's because of its atomic structure. I converse, for instance, with a person who works on planetary nebulae, Harriet Dinnerstein, and she can observe elements that in a rarefied planetary nebula that I can't possibly get in a star. And so, yes, it's an atomic physics limitation.
Okay. Question 6. What are the most important assumptions made in going from abundances to, some, let's say, surface abundances, so from the spectroscopy that we do with stellar atmospheres, to volume abundances, bulk stellar
maybe
abundances?
I did not understand the questions.
Yeah, okay. So you observe these shallow layers of a star. How do you go from there to the bulk abundance of a star?
That is, the point is that you don't, except in rare instances. the easy answer is that for any element that is subject, that can be synthesized only or mainly in massive stars, then as long as the star is somehow well mixed at birth, then what you see at the surface is what you will see in the interior. That's number one. For elements that can easily change during ordinary evolution, that is the CNO elements, lithium, light elements like that, you will see a profound difference between atmosphere and interior, depending on the evolutionary stage. You must make a model for mixing to account for that. As a matter of fact, the so-called S-process-rich stars, that they are very sensitive to the assumptions you make about what was in the interior versus what was in the envelope to be dumped out in space of the former companion stars. So it depends on the element. Those that can only be made in massive star syntheses, yeah, you're probably okay with saying, yes, these are the abundances that the star was born with.
Right. In particular for giants, when the mixing is deep. Yeah. Thank you. This last question is, what about the abundance of xenon, which, if I'm correct, seems to be an R-process element at the neutron-closed shell 82? Is it correlated to the observation of Europium?
I'm sorry, did you say xenon?
Yeah.
Okay. Again, you work in stellar spectroscopy, you worship the periodic table. Xenon exists on the far right column. These are the noble gases. And what do the noble gases do? Nothing.
Exactly.
It is very difficult to do any detection of any noble gas in a cool star.
In a cool star. So, and this answers the second half of the question: is it observed in ultrametal poor stars? Yeah.
No, never. Now,
Never,
as a matter of fact, one counterexample. Well, what about helium? You hear about reports of helium. The helium transitions that you hear about are ones that are signaling violent episodes in the outer atmospheres of the star. These are not normally normal standard absorption modes. So frustratingly, the answer is you can't do it.
On that happy note, I think my job is done, and I give the word back to Conrad. Thank you, Chris.
Thank you.